In this video, I want to take a look at limits of vector functions. What we're aiming towards is actually being able to do calculus with vector functions like we did calculus with functions of single variable with a single real output. And like I've said before, at least I think I've said before, Calc 3, we don't necessarily teach you any new calculus. We just teach you how to use it in higher dimensions with more variables and whatnot. And so this is the case that here, that we have a definition of limit, remember from Calc 1, that given a real valued function, f of x, we talk about limits in the following way. L is the limit of f of x as x approaches a. If for each epsilon bigger than 0, there exists delta such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon, right? You can make f of x as close to L as you want. Pick any epsilon, you can get it that close. If you can get it that close. That is, what do you mean by get it that close? That means for some values of x very close to a, for all values of x, I should say very close to a, that is less than delta away from a, then f of x will be close to L. Right? That was the definition we had for Calc 1, limit of a function. Now consider the following definition for the limit of a vector valued function. So given a vector valued function r of t, we define that the vector L is the limit of r of t as t goes to a if the limit as t goes to a of the norm, the length of r of t minus L, is equal to 0. Right? This is saying that r of t is getting close to L, right? The length of the difference between them is getting close to 0. Now, this is actually a reasonably nice way of doing it. I don't know if I've seen another book do it this way, but the book we're using does. And what it does is it turns a new concept into an old one, right? Because this, although it has vectors in it, this is just a real valued function of t. You give me a value of t, I can calculate the position vector r of t, a vector function r of t, subtract L, that gives me another vector, then take the length of it. Well, the length of it is just a number. So the process was you give me a value of t, I give you a number. That's a function. So the notion of the limit of this vector valued function boils down to the limit of the length of some other real, of some other vector valued function, but the length of that, so it's a real valued function. Now, the definition that I'm used to seeing is one that looks like this. Capital L is the limit of x, the limit of r of t as t goes to a. If for each epsilon bigger than 0, there exists a delta such that if 0 is less than t minus a is less than delta, then r of x minus L, length of that, is less than epsilon. This looks an awful lot like the definition up here, except that rather than having absolute value of f of x minus L, which is really the difference between f of x and L, the absolute value is just saying I don't care if they're in this order or that order, right? Take the absolute value, the difference will be the same. Down here, r of t, that should be r of t, shouldn't it? Let's change that. R of t minus L. Notice that this here is equivalent to this here. That is to say that this function, the limit of this function is 0, is to say that for each epsilon bigger than 0, there exists a delta such that if this is less than delta, then this, the absolute value of this thing minus 0 is less than epsilon. Well, this thing minus 0 is just this thing, and the absolute value of this thing is this thing because this is a positive number. This is the length of a vector. So this absolute value of r of t minus L is less than epsilon is the same thing as the limit of this minus 0. Well, the absolute value of this minus 0 is less than epsilon. It's the same thing. So this is equivalent. This definition or that definition are all the same. The point is, if you've got a vector function and you're looking for a particular value of t, what does it go to? You're saying, what's that vector going to? if you're saying it's L, then you can get arbitrarily close to L by taking T sufficiently close to A. Now, other textbooks use the following as a definition, and then they have a theorem. You either use this definition or you use this definition, and then you prove that they're equal to each other. So we're using this as a theorem. That either one of the definitions I have up there are equivalent to saying the following. That if you have a vector function, we're going to talk about the components now, f of t, g of t, h of t. Now, if I was just in 2D, I'd just do f and g, but I'll do it in 3D here, f, g, and h. And suppose I got a vector L with three components, Lx, Ly, Lz. And we say that L is the limit as t goes to a of r of t if the limit as t goes to a of f of t equals L of x, and the limit as t goes to a of g of t equals Ly, and the limit as h of t goes to Lz. That is, the limit of the vector function is the vector function of the limits, right? That is, you just look at each one. What does the x component go to? What does the y component go to? What does the z component go to? If all of those limits exist, then the limit of the vector function is the vector with all of those limits in it, right? And the proof of this is really the idea of putting spheres in boxes and boxes and spheres, which I will draw a quick picture of to describe here. So I have here, just in the plane, a curve, which I'm thinking of as a vector function. So at different values for t, you're giving me a vector that's pointing there, or maybe a different time t, it's there, and a different value of t is there. And we're saying as t approaches a particular point, a particular value, I think that the limit is that vector right there, okay? And to say that the function is getting close to that vector, by the original definition that the book gave, or my version of it, is saying close means when you give an epsilon, that's how close you want to be, that means you're drawing a little circle around it. That is, if you can land in that circle, you're close. And then you say, okay, well, now draw a smaller circle. Can you get into that? And draw a smaller circle. Can you get into that? And for each epsilon, you have a different circle. And you're saying, that's what I mean by close, that the function is getting close to L. Okay. On the other hand, the second definition, where you do it component-wise, look at the limit of the x component, limit of the y component, limit of the z component, you're saying, well, in this case, there would just be two things. You'd be saying the x component has to be close, so you're giving bounds in the x direction as to how close you think that is. And then you're saying, how close does the y have to be? Well, the y's got to be this close. So you're drawing a little box, a little square in 2D, or a little cube in 3D. Now, it doesn't necessarily have to be exactly a square. It could be a rectangle, or not exactly a cube in 3D, because the epsilons might be different in the three directions, but you have some sort of rectangle in 2D or box in 3D. And the idea is, if you think being inside that little box is what you mean by close, then that's fine. You can always, for any circle that you think is close, you can put a box inside, and if you're inside the box, then you're inside the circle. But likewise, for any box that you think is close, you could put a circle inside the box and say, well, if you're inside that circle, you're inside the box. So the closeness being measured by small boxes or small circles is really equivalent, because you can always well, you can always put a square peg in a round hole, or the other way around, as long as the pegs are small enough, right? So they're the same. But from the point of view of evaluating limits, that let's go back here. From the point of view of evaluating limits, this is going to be the way to go, this definition down here, because you can just look at individual ones. Now, for instance, here's an example in R2, in the plane, where I have a vector function 2t minus 7 and comma t cubed minus 9 over t minus 3. And I want to know what's the limit as t goes to 3. Well, according to the theorem right up above here, you can just look at what's the limit of this, what's the limit of that, and write that as the result. So if you liked doing limits in Calc 1, man, have I got news for you. I got good news for you, because now each limit is 2 limits or 3 limits, or however many components you have, because you just do the limit of each one. So here I'm going to take the limit of the first component, and I'm going to take the limit of the second component. The first one's really easy. Nothing goes wrong. Plug the 3 in. 6 minus 7 is -1. Right? Here it's a little more work because plugging the 3 in is a 0 divided by 0, which means either you got to do a factor and cancel, or you got to do L'Hopital's rule, or there were several methods we had, recall back in Calc 1. In this case, I'm just going to factor and cancel because I can, because it's just polynomials, and I know that if I've plugged a number in and gotten a 0 out, then it factors with t minus that thing as one of the factors. So I know t minus 3 is a factor at the top. Just got to find the other one. It's t plus 3. And the t minus 3's cancel out. That's the 0 over 0 problem. I'm hoping this is ringing a bell, or maybe a distant memory of a bell of how to do these limits from Calc 1. Cancel the t minus 3's out, and then you can plug the 3 in. T is 3 plus 3 is 6. And so my answer here is minus 1/6. That's the limit of this vector function. Now, the picture of what's going on here is this right here. Let's click on it to make it a little bigger. Actually, that picture wasn't quite right. I had a 3 typed in here instead of a 2 when I made that picture. So here is the correct picture. X equals 2t minus 7, y equals t squared minus 9 divided by t minus 3. And this is the graph. Turns out it's a straight line. There is, however, a hole in it at, well, it's hard to tell that it's t equals 3 because when you look at the graph, you don't see the t values. You see the x and the y values. But I have the t value down here. As I drag this, this slider along, you can see what the t value is, and then it plots the appropriate vector, and you can see that the end of the vector is always lying on this line. Now I'm interested in the limit as t goes to 3. So there's it at 2, 2.4, 2.5, 2.7, 2.8, 2.9, and it disappears when I get to t equals 3 because the function's not defined at t equals 3, right? The y value has a problem there. The x value exists, but the y value is undefined. So the vector is not defined at that point. But for every other value of t, I seem to lie on this line. And so the limit as t goes to 3 is exactly what it would be when you get to this point right here, which has an x-coordinate of -1 and a y-coordinate of 6. Okay, so there is that. Let's do one more example. And this is an example of a limit that doesn't exist. If you remember back to Calc 1, there were several ways that a limit might not exist. The left-hand limit might be different from the right-hand limit, right? So the function comes in at 2 different levels, and they're different from each other, so there isn't one value that the function is getting close to. There's 2 values depending on which side you come in at. There's also the problem of asymptotes, right? Vertical asymptotes, when the function's not even, it doesn't settle down to a finite number, it heads off to infinity or down to minus infinity. There was also the issue of sufficient squiggliness, right? That is, if the function comes in and it's going up and down so fast as it's moving in that it doesn't it doesn't ever settle down to one number. It just keeps popping back and forth between a couple different numbers. And so here's a similar example. What I've done is I've set up limit as t goes to 0, sine of 1 over t, cosine of 1 over t. Each of these in itself has a sufficient squiggliness problem as t goes to 0. This keeps bopping back and forth infinitely many times between 1 and minus 1 as t goes to 0, as does this one. However, for every value of t except t equals 0, this lies on the unit circle. That is, the blue arrow here lies on the unit circle. Now, what happens is, well, let's see what happens. It looks like it's not just the unit circle. You got all these lines running through the middle here. And there's a lot of weirdness going on. Let's see what happens as I drag this. Okay. See, this is moving around the circle. And it keeps moving around the circle. And it gets going faster and faster, and then it's going so fast it can't keep up with itself. It's jumping around too much, and then at the end you see it slowing down again. Individually, let's look at what the x-coordinate is doing. So I'm going to just say t. So here's what the x-coordinate is doing. The x-coordinate is just going back and forth between -1 and +1 and -1 and +1, and you can see through this section. Actually, let's just set it right here and say animate. And you can see this is increasing t at a steady rate, and so it seems like it's moving rather slowly along this curve. And so then it's still moving. The y-coordinate is increasing at a constant rate. Now the x-coordinate is going back and forth and back and forth and back and forth and back and forth too many times, and then it comes out on the other side. It slows down. There's infinitely many cosine waves back and forth here as t heads to 0. There's no limit. Likewise, let's put this back to cosine 1 over t and see what, so those, sorry, that was x, I have it as sine, well, whatever. It is sine and cosine, or cosine and sine, is still the unit circle, just which direction you're going around it. I want to turn this one into a t now so you can see what that looks like. So yeah, so this is the y, which I have it as cosines here. Again, let me pull this back to here and animate it. And you move along this sine cosine curve, I guess is what it is. And it goes between 1 and down to -1. Right there is -1, and then it goes up to +1, and then down to -1, and up to +1, and -1, +1, and then it works its way out the other side. So with the x-coordinate bopping back and forth like this, and the y-coordinate going up and down like this, you're tracing out the circle, and you do it faster, 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 infinitely many times as t approaches 0, and then infinitely many again and coming back out of it. And the net result is the graph is a circle, but all these lines going through the middle are because as it's plotting points, I mean, the way it draws it is it plots a point and then it increases t and plots another point and connects them with a line. And so each time the line is getting a little longer and a little longer, and then it's starting to jump across because it's going around too much of the circle and not hitting all the points in the middle. This actually should just be the circle, but because really crazy things are going on close to 0, it looks funny. As t goes to 0, the limit does not exist. There is not a single vector that this gets close to. It keeps moving around and around the unit circle infinitely many times. So anyway, there you go. There's a limit that does not exist. If any one of the components has a limit that doesn't exist, then the whole thing doesn't exist. In this case, both components, the limits don't exist. So there you go. There's an introduction to limits of vector functions.